Okay, so we're going to pick up talking about pyramids. We're still in section 11.4. And we just got through talking about prisms. Now we're going to talk about pyramids, which is a different type of polyhedron. So a pyramid is a polyhedron determined by a polygon, that is going to be a base, and a point that is not in that plane, this point at the top in this example, that we call the apex. And this apex is the point where all your sides intersect. So you can see, hopefully, you've got this outside triangle and this outside triangle, and then the one on the front side, and where they all meet is at that apex. And so all those are called the lateral faces. The polygon below the apex, the one that's directly below it in this case, is what we call our base. Now, it is possible that you could take a pyramid and you could lay it on one of its lateral faces, and you still have this same base. We're not going to get into that kind of detail, but that is a possibility where if you were to take this particular pyramid with this base down here at the bottom, you could actually flip that over on one of its lateral faces, but this base is still the base because it's the one directly above that apex where all those points are meeting. And so there's some more detail there, but again, we're doing introductory geometry, and so we're not going to get into all the details with that, but just know that is a possibility. So we have right pyramids. In a right pyramid, the lateral faces are congruent isosceles triangles. So think about that. Remember, we said isosceles means that two sides are the same. So in this case, this side and this side would be congruent, and this side also would be congruent to those. And so when all of those sides are, or all those edges, are the same length, they're congruent, then we have what we call a right pyramid. Now, we a lot of times will think about a pyramid as having a triangular base, maybe, but it could also have a square base. If you think about the great pyramids in Egypt, they all have square bases. And you can see that if you look at a picture of those, you can see how there are four sides, four lateral faces that meet at the apex. And that square base makes that a right pyramid. And so this is an example, this square pyramid is an example of one that's lying on one of its lateral faces, but the square is still the base. And so the base is not always just that bottom face. It depends on where your apex is. And it's obviously easier to see that when it's a different shape, square, pentagon, whatever. With a triangle, maybe it's a little more difficult. And typically we leave a triangle pyramid with the triangle on the bottom as your base. But it could be a different face. It's still considered the base, but it could be lying on its side. And so you can see that with the square pyramid. And then with the next one, the pentagonal pyramid, it's got a pentagon as its base, and all the other points, or all the other edges, are congruent. So this edge and this edge and this edge and this edge and that edge in the back, they're all going to be congruent. For a right pyramid, your apex is always in the center of that shape. Our book really defines it as the center of the circle that makes up that shape. So let's say that you had a square, just as an illustration. The center of that square is determined by the center of the circle that would go through all of these vertices. So that would be how we would determine the center of that square. And so what our book says, the way it defines a right pyramid, is the circle that would go through each of these vertices. And just kind of as an example here, I'll show you. that center point is directly below the apex. So this point and this point should be directly on top of each other in order for this to be a right pyramid. Because if that apex is shifted over some, then all your other side links are not, or your other edges are not going to be the same. And so it's important that we understand that for a right pyramid, the apex has to be in the center, directly above the center of that base. Now, another kind of polygon that we could see is what we call a truncated polyhedron. And this is where one or more corners have been removed by an intersecting plane or planes. The polyhedron is considered truncated. So, for example, in this first example that you see, you can picture that this is basically a pyramid, square pyramid, or rectangular pyramid with the top cut off. So we would say that it's truncated because that top has been cut off. In this next one, you can see that it's a cube, but with this corner cut off. Right? That corner has been just kind of sliced. Think about just taking a knife and slicing it. While you're at home, I have found that while my wife and I are at home, we're cooking more and things of that sort. So if you were to get some groceries, and let's say you buy a block of cheese, well, if you were to cut off a piece of that cheese, well, it may be a rectangular prism, and a rectangular prism, and you've cut off part of it, a corner of it, or a piece of it. Well, then you've truncated it. You've made it a truncated prism. And so you could kind of picture that if this were a block of cheese in this shape, and then you just took a knife and you just sliced off part of it. And so it would be truncated. And then you can see the prism there that has also been truncated where the top has been sliced. Again, at an angle, so it doesn't fit our definition of what a prism would be, where the top base is parallel to the bottom base, but it's because that top part has been cut off. And so when that happens, we consider it to be truncated. Now, a couple different types of polyhedra that we could have are what we call convex polyhedron. We're going to also have concave polyhedron, and then obviously regular polyhedron. So a convex polyhedron. We talked about convex and concave two-dimensional shapes previously. A convex polyhedron is a polyhedron in which the segment connecting any 2 points in the interior of the polyhedron is in the interior of the polyhedron. In other words, it doesn't cave in any. So most of the ones that we've looked at today, I think, have been convex. There's no place where it caves in. Again, you could see that. Again, I'll show you some examples of that in a few minutes. But if some of your faces are concave, then odds are you're going to have a concave polyhedron. But if it's convex, if they're all convex shapes, then it should be a convex polyhedron, where any line that you were to connect between any of the vertices is going to be on the inside of that polyhedron. Now, our next one is a regular polyhedron. This is a convex polyhedron whose faces are congruent, regular polygonal regions, such that the number of edges that meet each vertex is the same for all vertices of the polyhedron. Now, I'm going to show you an example of this in just a second. This would be if you were to take, let's say, for example, a polyhedron with triangle faces. Well, all of those triangles would have to be regular. And you may have done this before. Usually in a geometry class, this is an activity that we typically would do. And if we were in class, I would have you do this in class, where you take a polyhedron, you take a net of it, which we're going to define later, and you fold that piece of paper with those polyhedron or those polygons on it to make a polyhedron. And some are really, really neat looking, where all of those faces are the same shape and they're regular, forming a regular polyhedron. And then there's some that are concave, where you have maybe different shapes. It's still a polyhedron, but it can be really a kind of a wild looking shape. And so a regular polyhedron has all the faces are the same shape, same polygon, and they're regular. So equiangular and equilateral. So here are some examples of regular polyhedra. So a cube is a very common one. We know what a cube looks like. But every one of its faces are the same. They're regular, right? They're the same. They're congruent. They have the same angle measurements, the same side length measurements. That's what we call a cube. The next one is a tetrahedron. This is made up of 4 regular triangles. So again, equilateral and equiangular. And they're all connected. You can see that one there. The next is what we call an octahedron. Now, you may say, well, why is it called an octahedron? Well, the octa tells us there's 8 sides. And if you were to look at this one, you've got this side in the back, this side on the right side, the side on the left, and the side on the front, all of this. So there's 4 sides to that pyramid. Well, then the pyramid shape on the bottom also has 4 sides. And so each side is a regular triangle, equilateral, equiangular. And so it just happens to be that there's 2 of them kind of put on top of each other. Again, with that base being the square of each of those. And then here are some others. One is called a dodecahedron. And you could count the number of sides in it. You would see there are 12 sides on this dodecahedron. But every one of those faces, you can see this one at the top, is a regular pentagon. They are equiangular, equilateral pentagon. And when you put them all together, you end up with a dodecahedron, a 12-sided polyhedron. And then the next one is what we call it, it's an icosahedron. I can't hardly say that. But it has triangles that are its faces. And again, you could count how many there are. There's 1, 2, 3, 4, 5 on the top. 1, 2, 3, 4, 5, 6, 7, 8 around the side. So that's going to be 18 faces total. And so that one is kind of an odd looking shape. But again, all regular triangles, and there happens to be 18 of those. Again, I would encourage you, again, if we were in class, we would do this. I would encourage you to go find go just Google search for polyhedron and look at all the different types. And so usually there's an outline, a net of what it would look like if you were to open it all up. And then you can actually print that and cut it out, and you can fold it together and make your own. Again, if we were in class, I would have you do this in class, and I would have some examples for you, because I think they're really neat, and it's kind of a fun activity when you start making these polyhedron. These are all regular. All polyhedron don't have to be regular. These happen to be these examples I've shown you so far, but that is not always the case. Sometimes there are some that are concave. So I think of one where maybe it has some triangle faces and it has some rectangular faces, and when you put it all together and fit it all together right, it's kind of this spiky looking ball shape. And I don't remember how many sides it is, but that's kind of a neat one. It's hard to do when you're trying to fold it and all, but that would be a really neat polyhedron that you could do. So if you were going to teach this in elementary school class, this is going to be probably 4th, 5th, 6th grade type content. Well, you may want to print some of these and have your students make them in class. That would be a real fun, hands-on activity that your kids could do. Again, I would do that with you if we were in class together. All right, so let's talk about this little chart here. So what I like about this chart is it gives us a polygonal shape, interior angle measurements. It gives us number of polygons at a vertex, and then some of the angles at the vertex, and then what polyhedron would be formed. And so if you use a triangle as your face, okay, a regular triangle, each of the interior angles are 60 degrees. We know that because it's equilateral, or equal angular. If the number of polygons at each vertex is 3, then you have this first tetrahedron that you can see here at the top. And the sum of the angle measurements at each vertex would be 180 degrees. So if you were to take all 3 of those triangles coming together, again at 60-degree angles, all 3 of those would form 180 degrees. The next one shows that if we use a triangle, again 60-degree interior angles, but if you have 4 polygons coming together at a vertex, which is what you see in this second example, and you can kind of picture this, I hope, this polygon in the back, this one on the front, and then same thing on the bottom. You've got one here and then the one on the back side. And so you have 4 coming together. You could even see that here at the top, where you have 1, 2 on the front side, the one on the back side, and then the one on this other side over here. All 4 of those coming together. And so when you have 4 coming together, the sum of those angles is 240 degrees, and it forms an octahedron. And then for the third one, again, using triangles as your sides, if you have 5 polygons coming together at one vertex, like you do here, then the sum of each angle measurement is 300 degrees. So again, you can see you have 5, so there's a triangle in the back, there's another one in the back, and then you have this one on the front, this one on the front, and this one on the front. So you have 5 triangles coming together. The sum of their angles at each vertex is 300 degrees, and it forms an icosahedron. Now, some other common polygons that we have. One is the square, and we know what that looks like as the sides. 90-degree angles for each angle measurement on the interior. If you're using a square, typically a cube is what we're going to talk about. So you would have 3 angle measurements coming together. 3 polygons coming together for a sum of 270 degrees at each angle. And then, of course, it forms the cube. And again, you can see that in this first example. And then another common one is the dodecahedron. It has a pentagon for the sides. And you can see this one really well, especially here on the front side. You can see that pentagon. Again, if it's equal angular, all the measures are 180 degrees. Here we have 3 coming together at once. The sum of the angles at the vertex is 324 degrees, and it's called a dodecahedron. And I am not completely positive, somebody can check me on this if you would like to, but I believe a soccer ball is a dodecahedron, I think. A soccer ball would be an example of a polyhedron, because you know that it has that pentagon shape for each of those pieces, and I believe all of the pieces are the same shape and same size. I I believe that's right. So if you have a soccer ball, if you played soccer or have a brother or sister that plays soccer, or somebody that has a soccer ball close, go pick up that soccer ball and look at it. And look to see, is it a dodecahedron where you have 5 sides on each face, so a pentagon, and then have 3 coming together at once? That has to be if it does, it has to be a dodecahedron. And you can count the number of sides. I believe there's 12 different sides there. So if you wanted to make one of these, you could use these patterns, and you can find these online. All you gotta do is Google it. And these patterns are used to construct these different polyhedron that we've looked at so far. And again, there are many, 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 many others. These are just a few that you could look at. So the first one is the net of a cube. And you could imagine that if you take the 3 sides, this side, oh, not that one, and this side, if you were to take all of those and fold them up, and then you could take this side also and fold it up, and then this one would be your top. So you can kind of picture how that would work, right? In the tetrahedron, this triangle that's in the with dotted lines would be your base. And then you would take this one and you would fold it up, and you would take this one and fold it up, and you would take this one and fold it up. And all of those points here would all meet at the apex, that point of the pyramid. With the octahedron, it's kind of the same thing, where you're going to take this side and fold it up, and this side and fold it up. And what you're going to see is when you start doing that, you've got to make your edges line up on top of each other. And so that's where this 3-dimensional shape really comes in, and it kind of gets complicated because when you start folding it, you've got to get edges to line up. So, for example, this edge would have to lie on top of this edge. They would have to meet. And so this one gets folded up, and this one is going to get folded that direction, and so those 2 edges would meet. This edge and this edge would also have to meet. And so you can kind of picture what that would look like if you were to fold it. And again, I would encourage you, you're sitting at home, I know you got a lot of schoolwork to do, but you really can't go anywhere, don't have anything else to do maybe, go print one of these out and try it. I think it'll give you a better idea about what a polyhedron is if you actually go take one and make it yourself. And again, you've got a dodecahedron for the next one, so you're looking at like these 2 sides, for example, would have to line up and touch. You would have these 2 that would touch, and these 2 that would touch, and so on. And then when you fold it up, you're going to end up having this side and this side that touch. And again, you can picture how that's going to roll up together and be almost a circular shape, kind of like a soccer ball, but each of the sides are pentagons. And then the isohedron is very similar again, where you're going to take these outside triangles and you're going to fold them up. And then the ones at the top you're going to fold down, but you're not going to fold them completely down because again they've got to all come together. And so it takes a little playing with to get that exactly right. And the more shapes you have and the different types of polyhedron that you have, that can get a lot more complicated. And so again, I'd encourage you, go try to build one. If you do build one, take a